Okay, so in this video, we'll have a rundown on the theorem of infinite limits. So it's already written as shown in this picture. But before that, I'd want to write this down first. So for infinite limits, so we have limit of f of x as x approaches a. This is equal to, if this is equal to infinity, this basically means that um, there is an increase without bound. And in the same way, if we say that this is equal to negative infinity, then that basically means decrease without bound. Okay, so basically, the presence of infinite limits shows to us that a limit fails to exist. So this is usually denoted by an unbounded behavior of f of x as x approaches a. So I'll leave it at that. Let's start now with the theorem of infinite limits. So let's start with the first. So as x approaches 0 from the right side, and we have a limit expressed as 1 over x raised to r, such that r is any positive integer, that's equal to infinity. Let's say x approaches 0 from the left side, the same orientation, so it's a fraction, 1 over x raised to r. If r is even, an even number, let's say 2, x raised to 2, then it's positive infinity. But if r is odd, let's say r is equal to 3, then it's going to be equal to negative infinity. So what about the third theorem? So let's say x approaches a from the right or the left. So the limit of f of x is equal to 0. What if we have limit g of x this time? So either way, coming from the right or from the left. And turns out that it is equal to a positive or negative constant. So if we bring the limit of f of x and then this one basically being in the denominator and g of x in the numerator. So it could give us 4 possible orientations. That's the word I'm going to use personally. So we have a constant that's positive, and we have 0 below as a positive, so that's equal to positive infinity. That's easy. Negative constant over 0 positive, so that's going to be equal to negative infinity, similar to the policy on positives and negatives. So when we multiply or divide, if it's a positive and a positive, it's still going to be equal to a positive. But if they are opposite signs, or let's say this way, so they're going to all equal to negative. So same concept. Here, it's one is positive, the other is negative. So it's going to equal to negative infinity. What if both are negative? As shown in this scenario. If it's going to be positive. As easy as that. So, we all know, you're supposed to know that 0 positive is basically a very small positive number. Let's say 0.00001. For 0 coming from the left side, it's a very small negative number. So let's just say the opposite. But, well, yeah, the opposite with the notation of a negative sign, or denoted by a negative sign of the same number, 0.0001. Okay, for the fourth theorem, if the limit of f of x as x approaches a is equal to positive infinity or negative infinity, and for g of x, it's equal to positive or negative constant, if we plus or minus the both of them, f of x and g of x. So we also have various scenarios, but it's just common sense. You don't have to really memorize specifically. So it's going to be obvious. So Infinity plus a constant, that's obviously going to be a bigger infinity, or it doesn't basically change. Infinity is without bound, right? So if we add a constant, that doesn't change much. It's still going to be a positive infinity. If we have a positive infinity and a negative constant, we apply the same concept. So positive infinity is without bound, and we just have a negative constant. That doesn't change anything. So it's still positive infinity. In a similar idea, if we have a negative infinity and a positive constant, we'll obviously get a negative infinity. And if we both have a negative infinity and a negative constant, then that's going to be equal to the same thing, negative infinity. For the fifth theorem, so the limit of when you multiply both of them, f of x times g of x. So yeah, same concept, similar to the division that we've seen in Theorem 3. So positive times positive, positive. Positive times negative, negative. Negative times positive, negative. Negative times negative, positive. As easy as that. Okay. Vertical asymptote. The picture was kind of cut. But essentially, if f of x approaches positive or negative infinity as x approaches a from the right or left, then the line x is equal to a is the vertical asymptote. So I know, if I remember correctly, there is a condition that tells us whether a function has a vertical asymptote or not. We'll be encountering that in a different lesson. More specifically on transcendental curve tracing. So yeah, that's a pretty long way ahead. Let's first I'll first show all of the possibilities of what a vertical asymptote would look like. So let's say as x approaches a from the right side. So this is equal to positive infinity. Graphically, it looks like this. So this is your vertical asymptote. This is where a is in the x-axis. And essentially, your vertical asymptote looks like this. How about as x approaches a from the right side, but this time it's equal to negative infinity? What would the graph look like? So same thing. This is a. Asymptote would look like that. Okay? And that's basically the portion where the picture was cut. The rest, the two others, are these. So, compare. Actually, I think it's less confusing if I orient it like this. Okay, so as you can see, both are positive infinity, but what's the difference? So, coming from the left side, so obviously we come from the left. But here it says coming from the right side, so other right side. I hope you see the pattern. And negative infinity, both of them are bound downwards. And if we say coming from the right, so bound downwards from the right. Coming from the left, that means bound downwards from the left. Okay? So that's basically it for vertical asymptotes. Okay. Limits at infinity. So the limit of f of x is equal to L as x approaches positive infinity. And we also have the limit of f of x is equal to L as x approaches negative infinity. This is where y is equal to L. So this is the horizontal asymptote of the graph. So earlier, we've discussed about vertical asymptote. This time, let's talk about the horizontal asymptote, or denoted as an abbreviation HA. So this is the horizontal line that a graph approaches but never touches as x approaches infinity or x approaches negative infinity. So if you want to determine the point of intersections, you'd want to solve for x for f of x is equal to L. So yeah. I also remember in transcendental curve tracing. No. Not in transcendental. More on piecewise functions, how you would graph them. I'm just not sure if I remember it right, but either the vertical or horizontal asymptote, you could determine if a horizontal asymptote is equal to 0, is equal to the coefficient of the term with the highest degree of polynomial, if that makes sense. I'll demonstrate it later. Or basically, HA does not exist. I think it's clearer to me now. I think it's we're talking about the horizontal asymptote. So basically, let's say x raised to 2 is equal to x. How would you know the horizontal asymptote of x squared over x? Since the degree in the numerator is greater than that of the denominator, so y is 0 basically. And let's say the degree of the numerator and the denominator is the same. Both are raised to 1, right? So in that case, if the degree is the same, the horizontal asymptote, I believe, would be 3 over 2. You just copy the coefficients in that fashion. And when the horizontal asymptote does not exist, we see it if the degree of the numerator is less than that of the denominator. So let me just confirm if that information is correct. I hope I still recall my math correctly. It's been more than a week since I took the differential calculus test. Fortunately, I passed the course. The test was 30% of the final grade, so that was very risky. Okay, I think what I thought was the other way around. It's not supposed to be like that. Let me just confirm. Okay, so let's start matching. So if the degree of the numerator is greater than that of the denominator, horizontal asymptote does not exist. What if it's the other way around? X over x squared. Okay, so clearly, the horizontal asymptote, if it's the other way around, that's equal to 0. Always 0. As long as the degree of the denominator is greater. Always 0. No other number. If it's 3x over 2x, the horizontal asymptote would be 3 over 2. That is correct. Okay. I hope that doesn't apologize for the confusion. Good thing I still remember somehow. Okay. Theorem of limits at infinity. So let's say R is a positive rational number. So therefore, limit of 1 over x raised to r as x approaches positive infinity is equal to 0. If r is defined when x is less than 0, then the limit as x approaches negative infinity of 1 over x raised to r is 0. Okay. Can't really elaborate more on this. Okay. This is what I was trying to say a while ago. I hope it's not too late, but this is what it is. Okay. So yeah, that's it. Next lesson. Squeeze theorem. So there are two things that you'd want to know on squeeze theorem. Actually, let me just write it. So this is in other words called sandwich or pinching. So basically, if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x in an open interval containing a. Also, another condition, if the limit of h of x as x approaches a is equal to L is equal to the limit of g of x as x approaches a. So the limit exists. And this is equal to L.